Okay, continue. Today we have chapter 10. We have polymer, ceramic, and composite material. Today we try to complete chapter 10 with ceramic and composite. All right. So for today, we try to complete either ceramic, and then tomorrow we complete composite. We try our best, lah. Best. Right. Okay, we go into ceramic. Go into ceramic. Now, what is ceramic? Ceramic, things that you can think of will be like flower, container, all these there. So they are inorganic, ceramic, they are inorganic and non-metallic material. So far, before chapter 10, you can say 1 to chapter 9, we are always deal with metal component. But when it comes to chapter 10, we go into polymer. Polymer is not a metal material, but ceramic is a non-metallic material and organic, right? It can be mixture between metallic and non-metallic. Yeah, so they have two type of ceramic material. Traditional material or traditional ceramic material. You have clay, silica, feldspar, all these, right? So it's the one that you see in your hotel toilet or your house bathroom, tiles and all these. So all these are traditional ceramic material. Another one is a structural ceramic material. So this one is more advanced as the technology become more and more and the science knowledge become more and more. Then we will apply the knowledge to create a component that able to sustain higher pressure, higher temperature, and so on. So they are named as structural ceramic material. They will be using like aluminum oxide, AlO3, silicon carbide, silicon nitrate, and so on. So the main idea is that ceramic material can split into two, traditional and structural. Right? So what are the properties, right? So again, we are in an engineering program. So most of the time, we are more interested in their properties, and then how we apply the properties. The question or in your assessment, the question will always be in asking you what is the properties and then how you apply it. Okay, so when you calculate the value, then the question will ask you what mean by the value or how you apply the value. Right? You're always like that. So ceramic material properties, you think of all those tiles, they are hard, they are brittles, and they are low toughness and ductility. Low toughness means they are not able to sustain tensile forces. Means if you go and pull the tile in your toilet, they easily break. But if you compress or you try to compress it, then they're able to handle the compression test. Okay. Traditional, structural, they still exhibit the ceramic properties, but they are more have better material, have better mechanical properties compared to the traditional one. Okay, because they are still ceramic. Okay. So why we need to study ceramic material? Because nowadays we are in an IoT era, Internet of Things. You're using handphone, smartphone, computer, tablets. Inside all these electronic component, you have all the resistor, all the transistor. So ceramic material, they are good in electrical and thermal insulator. Okay. Okay. Then they have a high melting temperature and high chemical stability. So these are the advantages compared to the metallic material. So ceramic, they are insulator of electrical, and thermal. So they're able to insulate, protect the component from heat. They able to sustain high temperature and chemical exposure. So it means they are high chemical stability. So when you think of these two properties here, you can think of their application. Anything that near to high electricity power, anything that near to uh, high temperature, then very high chances you will see ceramic material, right? Engine block, your computer. If you have a laptop, your computer, you have a heat sink, all these things, right? What else? If you're in a aerospace, then you have the cover for the rocket. When it go through the atmosphere, it will generate heat and so on. Okay, so this ceramic. And in the ceramic, you have ionic and covalent bonding. So this table, it will tell you what are the crystal structure, right, and the formula of each type. So we just glance through because it's in the table form. So all these, they are ceramic material, and their melting point is a bit higher compared to metallic material. This is what I want to highlight. The temperature will be higher than the metallic material. Okay. And this one is another table for ceramic material. How you identify whether it is a ceramic material or it's within chapter 10 question. You look at the name, you already know already. Carbide, oxide. Major ceramic, you will have carbide, something oxide, right? And then something oxide, something oxide. So they are very easily to identify as silicon or ceramic material. So you can see the bonding, electronegativity difference, percentage of ionic character, covalent character. So there is a calculation to calculate percentage. Also for ceramic, later there will be equation to calculate the ionic character, covalent character. Okay. So these two, percentage of ionic character and covalent character, this one, it will tell you the chapter 1, chapter 2 crystal structure. These two will affect the type of crystal structure that will form. Okay. So what affect the arrangement of their ionic? So there are few factors. So I'll give you all. Okay. First is, again, the size of ion. And then the second one is electrostatic charges. These two will tell you how ceramic material, the packing of the ion, how they're going to arrange the ion. So first is the size of the ions. Then you need to balance the electrostatic charges because you want to get neutral. There is no positive charge or negative charge. You get 0 charges so that it's stable. Okay, two things. How you arrange the packing of the ion, size, and electronegativity or electro charges. These two. Okay. Then there will be a size limitation for pack. So it's like you want to pack something into a crystal structure. There's a limit there that you can fit. So before in I think in chapter 9, you learn about coordinate number. Okay, what I mean by coordinate number? Coordinate number is, let's say, in this crystal structure. So let's say we have BCC. BCC, you have one single atom inside, and then you have eight atom on top and below, right? So if you focus on the middle atom or middle sphere, this sphere will contact of 8 sphere. So for this atom, the Cn will be 8. Okay, when it contact with how many sphere that these particles contact. So the Cn number is 8, for example. Right. So you can see the definition here is correspondent to the number of nearest neighbor. Um, so it's important when you do calculation later for Cn, you need to identify which atom that you are looking for. Here, this atom may be different. So you need to like imagine how they form or how they pack. Okay? Because when you pack the atom, the crystal structure must be same, right? So it's like building a Lego. Then you need to imagine how the atoms being packed. Okay, so they are stable and unstable, as you can see on the screen. If there is a gap that fixes the dark blue color atom, then it becomes stable. Means it's not able to move up, move down, left, right. Right? Then it becomes stable. Same with this one. One on the left is bigger, smaller, but still the middle one cannot move, so it becomes stable. But if the atoms, for example, you include nickel, Ni, nickel is very, very small, then nickel can be run along all the space there. So if you have this scenario, it becomes unstable. Okay. So by looking at this one, how we ask you in chapter 10 question. So normally we'll ask you to calculate the radius, the space you have. Then I ask you, give you a table, element 1, 2, 3, 4, 5, 6. Then you choose which atom or which element 1, 2, 3, 4, 5, 6. Which atom will give you a stable ceramic sample. So you calculate the size that you have between the atom and atom, right? So you have a crystal structure, so you draw a diagonal. Diagonal, you have a vertical and horizontal dimension. You have this one, so you can able to calculate the diagonal here, right? Right angle triangular. You have A and B here. You're able to find a C, right? So A squared plus B squared equal to C squared. You find this one, then you are given the radius of the holes. So holes, this one. Then you calculate the remaining space is here, right? So you're given the radius of this one, this one. Then you minus the C that you calculate. You have the space here. This is the diameter. Again, be careful on the radius and diameter terms. If the question give you radius, then you have to times 2 because you want to get the diameter. Okay, just be careful on that radius and diameter. Okay, same with this one and same with this one. So if you look at the table, the size is have a very big gap, then it becomes unstable. If too large, also unstable. Cannot say unstable, it's that you are squeezing the space there. You are giving a stress to the surrounding Okay. This is okay. Here we are looking at ions. We're looking at ions. So the two stable cases here is a coordination of anion around the center of cation. Right, cation is positive charge. Right. So this is all these are negative charge and then positive charge. Yeah. So based on the slides, this is positive, negative, negative, negative. Okay. So you have the one logic that I always apply is that electron is the one that can go around, right? And positive, negative always attract to each other. So you always positive charge always attract negative. Okay. So this ion, and if ion do not touch the central cation, then the structure become unstable. Then we start to do some calculation. We call it radius ratio. Radius ratio definition is ratio of the radius of central positive charge to the surrounding anion. It's called radius ratio. So you take positive charge radius divided by negative charge radius. Okay, positive divided by negative. So you'll tell you the radius ratio. Or positive or negative. Huh? So we want to try to find a stable combination. So when you have stable combination, there is a one cases called critical radius ratio or minimum radius ratio that it will give you stable on stable cases. Huh? Okay, so normally the question will give you the critical radius ratio or minimum radius ratio. So there's a number there. If is a radius ratio minimum, mean this one will give you the stable ratio lah. Okay. Okay. So if you're given a table something like this, then by calculating the radius ratio, this one positive divided by negative, you get a number, right? You know that maximum number you can get is 1, minimum is 0. So how you get 0? When you have negative that is very big number, you divide a number, you get a very small number. So if you get a small r negative, then you get a very big radius ratio, right? So people already done experiment and then they give you a simplified table. So if you get a number more than 0.7, your Cn is 8. Cn is again is how many molecules get contact with that sphere or positive charge. If your radius ratio is more than 0.73, more or equal, there is a dash there, more or equal, then your Cn will be 8. And this combination, they are named corners of cube. So they are cube, then corners, so you have 8. Right? It will be like this. Then if your number 4, 0.4, 0.4, then it will be 6. It will be something like this lah. Okay, it will be something like this. A corner of octahedron means the surrounding the positive charge will be 6. 6. Then the rest, you look at the number, you have how many Cn and so on. Okay, then you might get a number, let's say 0.5. You get 0.5. So 0.5 is which one? If you get ratio, get a ratio of radius, you get 0.5. So what is the Cn number? It's is confirm 6. Okay, so it haven't reached 0.7. So it's not 7, but confirm is 6. Okay, confirm is 6. Okay, yeah. So you have 3, 4, 6, 8 lah. So this is another table that is more colorful but still same, right? So it give you 2, 3, 4, 6, 8, something like that. So like for example, you get 0.5, you have 6. Okay. Okay, let's look at how we apply the ratio numbers. So calculate the minimum ratio, radius ratio for triangular coordinate CN3 of 3 anion or 3 negative of radius surrounding a central cation of radius r in the ionic solid. So this here, it did not give you the numbers, but it give you the very simple formula, which is r and a small r and big R. So you transform the question into a diagram. So it give you read again, it give you for a triangular coordinate 3 of 3 anion of radius surrounding a central cation. So means that you have 1 atom inside surrounding by 3, because Cn is 3. Cn3 means 1 in the center surrounding by 3. Okay, so you draw this diagram. Then you draw a triangular. Okay. Then again, recall what is the the formula to calculate the radius ratio. Positive charge radius divided by negative charge radius. So which one is positive, which one negative, you have to be sure. Center one is positive, surrounding one is negative. All right. So in the question, it do not give you exact number, but it give you a R, big R and small r. So small one is a small r, big sphere is big R. Right, here to here is big R, here to is big R. Okay. So the rest you read. So you have a triangular, right? So the length of here to here is R, here to here is R, so here to here is 2R. C to B also 2R, A to B also 2R. So you have a same side triangular. So same side triangular, 180 divided by 3. Each of the side is 60 degree, right? So we calculate the angle of DAE DAE over here is 30. So I enlarge it, extract here this triangular in the big picture. So D to A, B is here, center of positive charge. So positive charge to the outer radius is small r. And then the big negative charge from the center to here is big R, here to here is big R. So the right angled triangular, the hypotenuse AD will be R plus small r. Then this is 30 degree. You already calculated because half of the triangular. So you get 30. And then AE, A to E is the radius of your negative charge. So you have R. So AD is R plus 1, R plus big R plus small r. So cos 30, cos is side divided by hypotenuse, R divided by this one. Okay, so cos 30 is 0.866 something plus R divided by R plus R. AE is R. Okay, then you rearrange the equation. You pull the denominator to left hand side. Okay, then you get relationship between R and R. Okay, then the question asks you to find what? Critical radius is this one. Positive divided by negative. In this case, your positive is small r, negative is big R. So you take the numbers, you rearrange, you get the ratio radius equation. You get 0.155. Okay. So this is this is the first example, like how you get the ratio, even though you're not given the, the exact number of radius. So you try to ask yourself, if the question reverse the question, you're given the ratio, are you able to work back this CN number? Or are you able to use this one and then calculate the radius or combination of positive charge, negative charge that you can use that give you this ratio or give you the CN3? Okay, so radius 0.155, if you refer to table just now, this one, 0.155 just now is less, 0.155 is 3. You'll get 3. Okay. Or the question can be reverse engineer. It give you a coordinate number, then you estimate what are the combination that you can use. For example, it give you 3. Minimum number is 0.155. We don't go for 255 lah. We pick the minimum number, then you calculate the big R, small r. Okay. Okay. So when you do revision, try to think how your lecturer asks you, or how the question can be reverse engineer and ask you from the answer back to the question. Okay. Okay. Second example, you predict the coordination number if you're given the exact number now. Okay. The exact number now is just application of the radius ratio equation. So you're given the ionic solid CSCl and NaCl. Use the following, predict the CN number. So you calculate the ratio, then you refer to the table. Okay. So the first one is quite direct. So here, of course, you have to identify which one positive, which one negative lah. So if you look at the formula, normally the first component is positive, the one at the back is negative. Okay. So the first one, CSCl, is CS 0.17 and 0.18. Okay. So ratio, you just put in the numbers. CS divided by CL, 0.17 divided by 181. So you get 0.94. Based on this one, you refer to the table. Okay, refer to table. So table give you 0.4, 0.94, you refer to here is more than 8 lah. More than 0.73, so it's 8 lah. Okay, very direct calculation. No complex things. Okay. Okay, so can you estimate the second one? Can you do the second one? NaCl. NaCl is which CN number is what? Based on this table. What ratio number you get? 0.5 564. Okay, if your answer is more than 0.4 but less than 0.7, it will be 6. You see this table, if you see this table, confirm you need to use this equation already. Okay. Okay, so the answer will be 6. Okay, will be 6. Right. Okay, any question? Very direct, right? Okay, then processing of ceramic. I will just give you the information lah. Okay, process is to mix water and sand, and then you become the things lah. Okay, you have powder means yeah, powder, then you shaping, drying, firing. You dry means you left it in the room temperature, then let it evaporate all the water, and then firing, you put into a furnace, you heat it up, right? So these are the microstructure that you have lah. Okay, when it's a powder, then you have a loose powder, then you mix with water already, then the particles or powder will group together. The water will go inside between the powders, and then when it dry, then all the powders will agglomerate, or they will arrange in a certain sequence, but they still have a hole there. That's why ceramic, they able to cool down water. They're able to keep water very cold because of these holes here, right? And then the fire. Okay. So all this go very fast, right? Go very fast. Material preparation, you blend it and so on. Then you forming or casting. Forming means you put into the die, and then you duplicate the shape that you want. Okay. So there's a cold forming, there's a slip casting, extrusion, and all this lah. Okay. Pressing, dry pressing, and so on. So pressing is something like this. So you press the thing. Forming is the one that you learn in your previous chapter for metals. So still the same method, but now you change the material inside with the ceramic, right? So AB is filling, then you press, then you eject. Okay. The furnace will be something like this. Same like the metals material, you put inside there, let it become dry. But metal, they will melt lah. Yeah. So this is a pressing lah. There's a pressing, isostatic pressing. This one, I can't remember whether I asked you. I don't think so. I asked you this one. Okay, hot pressing. There are some hot pressing means you input high temperature, then you press it. Okay, something like this lah. If you work in the industry, the machine that provide the heating and the pressure at the same time. Okay. Ooh. And slip casting. Slip casting is a very traditional way. If you go to those cultural village, they will show you to the tourists how they make the traditional ceramic vase. So they pour in the slips and then let it cool down a little bit on the wall. Then they drain out from the mold. Okay. Then they do the natural drying, or they put into the fire. Just let it become a solid vase. Okay. The rest you read lah. The rest is still the same. This is more complex diagram, right? So if you do your FIP in this ceramic processing, then you need to go through all this process. Okay. Extrusion is something that you push inside there's a die there. You push your material, then you go through a certain shape lah, extrude. Thermal treatment, sintering, and all this. Okay, this one you read, huh? Sintering is important process for ceramic. Sintering is you heat it up, then you bond the particles together, right? So something like this lah. So there's a formation of net when you have two particles, then they will combine the two particles with necking. Okay. They will join, become one particles like. So this under microscopic. What else? You'll see like they are combined together lah. You see the shape like combined together. Okay, there's a new term for engineering student. It's called vitrification. Vitrification is gas phase liquefies and fill the hole in the material. Okay, the liquid gas phase may also react with some remaining solid. So, so you have a viscous elastic liquid, then you will have a crystallization. You also have glass transition. So you have either you get semi-crystalline or glassy solid lah. Vitrification is something linked with the glass phase because you have a silica, SiO, silica oxide, SiO inside. So silica is like a glass. So when you melt glass, then you will form something like that lah. Okay, so yep, let's watch the video. Oh. This is a 9 minutes video. I don't think we can go to the full videos lah. But this one is a very high-tech factory. I think it's worth sharing lah. It's worth sharing. I'm not sure whether Malaysia have this one. Sure. Maybe there is lah. Maybe there is lah. Glazing means you spray the sandblasting, you make it smooth. Usually those working in this factory, you are get paid very high because the occupation hazard because of the fine particles that you work every day. Okay, they compensate for your health lah. Okay, so don't you need to consider when you work in all these factory. They pay you high pay because of some of the occupation hazard. You need to consider. Okay, the rest you can watch after class. So again, mechanical properties is our focus in our mechanical program or engine program. So if you look at this one, the density, the strength, tensile, and the fracture toughness, and so on. So there are some calculation to get all these parameter. Factor that affecting strength of ceramic is mainly because of structural defect, or there's a hole there, or there's impurity, or there's imperfection inside there. Yeah? So this diagram tell you it tell you very direct by graphic. So you have a pores means hole, you have inclusion, you have a layer of crack, you have surface damage, you have unjoined edge, you have crack into ceramic, you have interface flaw. So basically these are all the defects that might affect the mechanical properties of the ceramic materials. Okay, so these are all the sources, right? So normally this kind of if this section normally come out in the section A, that they tell you ask you about some theory about ceramic. Then you tell the defect, what are the defect, and then you draw the illustration of the defect. Okay. Okay. you know that if you have holes, it's not going to contribute a lot to the strength. Right. So as you can see here, the transverse strength drop as you have more poles. There's more holes that you have between the particles. So also have the strength of material, chemical, microstructure, surface, temperature, so on. Okay, now we start to go into a bit calculation. Okay. So ceramic, again, they are combination of covalent ionic bonding. So they have a very low toughness. So there is a calculation to calculate the toughness. So fracture toughness test, you calculate the KIC point. Okay, so you learn about KIC when you study about metals. So similar. So we have a 4-point bending test. 4-point means there is a 4 fixed point on the ceramic, and then there's a called the line, the hole here. It means you remove some material here. Okay, then you knock from here or here, right? So there's a toughness equation same as you learn in your metals fracture test. KIC equal to Y sigma square root pi A. A here is the H defect or H of your holes lah. Okay. Again, your hole size you have two. You have two scenario. One is the H one. One is at the center of the object. This is 2A. You only use half of the radius. Okay, be careful on using this formula. Okay, we go through example 3, then we have a short break. So you have a ceramic material, strength given, fracture toughness given. Observe the fracture toughness unit, megapascal square root meter. What is the largest internal crack for this material can support without fracturing? Use Y equal to 1 for fracture toughness equation. So again, what is the fracture toughness equation? KIC equal to Y sigma pi A, sigma F. So where to get KIC? The question asks you the internet crack. So this is silicon nitrate ceramic. Give you the failure sigma is 300 megapascal. Here is mega. Remember to change mega into 10 power 6 in your calculation. Same with here. This is mega. So KIC is 3.6 mega. Mega is 10 power 6. Remember to transform the unit into unit SI. Okay. Y equal to 1 because question give you 1. If the question forget to put in Y in your answer, you write assume Y equal 1. Okay. So you have KIC, you have Y, you have sigma. Then the only missing parameter is A. Right? You won't see any formula in the assessment. You will see graph. You will see graph. Because it's very easy. Not very easy, very simple formula. And there's a chance for you to score marks also. If we give you solution, give you the formula, normally the question will be harder. Because you have all the information. So we are if you give you all the formula, the level of assessment will be higher. We will test you on application of value already. Then it will be harder lah. Okay. Okay, so you rearrange, you substitute value, you'll get 4 point something minus 5. You can put in micron. It is 0.4 micron. Huh? It's a unit. It's a unit. KIC is a unit. So you do the, have you studied how to do the dimension analysis? Dimension analysis, I think in I'm not sure which module, but there's a module teach you how to do dimension analysis. So KIC, if I transfer all the value, y, sigma, and pi a, y is no unit, y is a number. This one is stress. What is stress? Stress is force divided by area. So you what? Newton over meter square. Then you have square root. Square root pi is the number. A is length. The length. Length is meter. So you cancel all the things. So here you have Newton meter is Pascal. So here you have square root of m. So it's a unit. Okay. So here the largest internal tract. Here is a tricky question. So don't stop here because the question asks you internal tract. Internal crack. Internal crack is this one, not the edge one. So internal edge, you need to multiply 2 of your answer. So your 2a equal to 91.6 micron meter. Pay attention. So this one, it asks you internal, not edge, not the corner crack, not edge crack. So here I draw on the whiteboard here. This is edge, this is internal crack. So the question asks you internal crack. Okay, stop here. We continue 9, 10. 10 minutes breaks.